Good day, everyone. My name is Ryan M. Paradina, an MSEM student from Mapua University. I am here to present you my paper titled Particle Scrap Reduction of an Automotive Camera Product by Lean Six Sigma DMAIC Approach. So first of all, throughout this presentation, please bear with my voice because I'm currently sick while recording this video presentation. On this slide, we have our pointers to present. So as you can see, we have three. We will be discussing first the introduction and problem definition, and second, the DMAIC approach itself, a case study for the particular camera project F, because during this research, I use actual data from this project. And lastly, um, we will be having our key points through conclusions and limitations. Introduction and problem definition. First, I would like to discuss first our product, which is the automotive camera. One of the automotive or innovative safety features in today's automotive environment is by having cameras installed in your car or vehicle. So this is the sample of the camera, front view camera. The concept of automotive cameras is not only for giving display to user, but also provide solutions to different problems, especially the safety and security purposes. So here, on this picture, I'm pointing out an actual sample particle seen on actual lens camera. And later on, we will identify what are the problems encountered. On this slide, we have four problem identifications. First, any high scrap rate from production process only means there is something wrong that needs to highlight and escalate in order to have management actions and solve it by planning an improvement strategy. Second, the effect of scrap rate not only affects the profitability of the company, but also it reflects the image of the company overall. Third, a particle defect is any foreign material on top of the imager that was shown previously on my slide picture of it, which obstructs the optical path and hampers the vision of the camera. And lastly, one effective approach in this study is to use the DMAIC methodology from Six Sigma concepts. Of course, we have our goal, objective, and purpose of this study. So the purpose of this study aims to reduce the particle scrap using process improvement and identify a particle defect during the production using the DMAIC approach that will be prevent it to send it to the OEM or the overall equipment manufacturer or the end user itself. This will be also beneficial to anticipate any camera particle rejection and follow the recommended solutions and reaction plan. This paper will contribute to the automotive camera particle defect study using the DMAIC approach that will benefit manufacturers of automotive cameras by providing enough data and knowledge at different perspectives. Also, this paper will aid understanding how a particle is observed during the production process. Improvement actions are based on the results and validations of this study, on which the next researcher can use this platform to expand and elaborate further the next study. One of the first real case study in the automotive camera in the Philippines. DMAIC, a case study for Camera Project F. This is a company-based study. For the defined phase, I've gathered all the reject data for this particular camera project F, specifically on a certain model that I used to focus on this study, which I collected it from the production. As you can see on this graph, the total scrap rate is 4.4%, and out of it, 1.35% is the highest that pertains to the particle scrap. Consequently, the particle scrap cost is estimated at $2,000. As you can see here, I provided picture or illustration for us to have a better understanding. So this picture illustrates theoretically how a particle can be described as any foreign material on top of the imager or lens that obstruct the optical path and hamper the vision of the camera. In order to understand the measure phase, I presented here the step-by-step or the camera back-end process assembly flow. So here, you can see that there are a lot of processes, but the particle defect was trapped in the focus verify one, which is highlighted here in red. So this is a specific tester that will verify the focusing and alignment of the lens and image sensor. And here, we can obviously see the lens particle defect. After the define and measure phase, we now come up with the analyze phase. So on this phase, we can now dig down more details regarding the analysis of the high particle scrap. So here, I presented here a tree diagram regarding the high particle scrap. So as you can see on the yellow ones, there are four categories listed here or illustrate. So over rejection on particle trap during lens and imager assembly, particle inherit of lens, and particle inherit of imager. So based on the analysis, which can be further read in my paper, um, I've identified seven root causes of this high particle scrap. So it was, as you can see, it was number one, customer specification is too tight, any visible particle is reject. Number two, airborne particle drop to imager during staging. Number three, upright position of module during cleaning. Number four, current FA2 area layout is open for man and material movement. And then number 8 here, damaged blister with scratches stray from supplier. And number 10, one cleaning chamber used for different processes. And lastly, escape from vacuum filter. After the analysis, we can now focus on the improvement on the true causes. So first true causes is the airborne particle drop to imager during staging. So I used here two proportion test, and the result is that 22.54 reduction on particle defect. So the improvement here is that it reduced the batch cleaning quantity from 32 cameras, 2 carousel that is showing in the picture, to 16 single carousel. Second, transfer the clean cameras to class 100 clean room controlled environment. For the second true causes, or true cause, which is the damaged blister tray with scratches from supplier. So again, I performed here two proportions test, and the result was 21.33 reduction on particle defect. So the improvement here, remove the activity of transfer of cleaned lens to blister tray, instead proceed with final assembly process. So this is a sample of the picture how to do that. Third true cause, upright position of module during cleaning. Again, I performed two proportions test, upright and downright position, and the result was 23.61 reduction on particle defect. So the improvement I've done here is that modification of existing, cleaning of chamber with unit position downright outside the chamber. So this is a sample of how we do that on this picture. Fourth true cause is the escape from vacuum filter. I performed two proportions test, and the result is that 82% reduction of particle defect. The improvement here is that our group replaced vacuum machine with different filtration stages. So as you can see here, this is the illustration of replacing the vacuum machine with different filtration stages. The fifth true cause is the customer specification that is too tight. Any visible particle is rejected right away. So from here, I perform a different between appraisers and all appraisers versus standard. So the result here is that 7.47 reduction on particle defect. So for the improvement done here, send particle images sample to customer and let them decide for the acceptance criteria. So from this true cost, the improvement is that with the help of the customer, in order for them to identify and lower down the criteria for the particle defect. For the sixth true cost, the current FA2 or focusing and alignment 2 area layout is open for man and material movement. So I performed two proportions test and the result is that 23.61 reduction on particle defect. So what improve here is to enclose the class 10 or class 100 final assembly area and provide specific in and out location. So this is the sample illustration. And last true cause is the one cleaning chamber used for different processes. So again, I performed two proportions test, one cleaning chamber and the individual. The result is that 11.54 reduction on particle defect. So the improvement here is that we had fabrication of additional cleaning chamber. So as you can see here in the illustration, we have the PCBA air blow and USW or ultrasonic air water blow that is already present in the production line. And the additional cleaning chamber was beside of it, which is the lens air blow. After the improved phase, we now come up with the control and standardization of the improvement in order to ensure compliance and continue to reduce the defect particle scrap. So under the what column, so we have listed here the 7 improvements and how this will be worked on the second column. Third, where or is the location that will be performed, or where is the location that this improvement will be controlled and standardized. For the when, as you can see, this is already passed and we already completed this before in December 2020. And then the reason for the column why. Why are we doing the control and why we are doing the standardization. Conclusions and key findings. The key findings of this study mostly circulates on the DMAIC approach, or the Define, Measure, Analyze, Improve, Control, which use as a structured methodology to understand the particle defect and reducing it by improving the process. Second key findings, the root causes are 7 validated significant factors that are true causes, namely particle escape from vacuum filter, one lens cleaning chamber used for different processes, damaged blister trace from supplier, current alignment tester area is open for man and material movements, upright position of the module during lens cleaning, airborne particle trap imager during staging, and lastly, customer specification is too tight for particle criteria. The results are effective based on using the two proportions test to determine whether two groups are differed. It provides 8% reduction improvement on the particle reject from the reference root cause data. And last key findings is that for the future research related to this study, there is need to expand the horizon by considering other camera model application, not only automotive cameras, in order to broaden the knowledge of the particle analysis. I have 4 limitations on this study. First, The limitation of this study are that the data was collected on a 1 month only duration of the camera assembly line production. Second, for the two proportional test, the simulation is based on the actual data gathered from and to using two proportions test. Data can have some variations on the actual execution since different operators were given the task to do from the reference problem up to the recommended solution. Third limitation is that the study only focus using a single camera model, wherein it is the prime model of the camera project F. And lastly, setup of the machines. Change setup of the machines like testers can also be limitation, since this can be changed over and set up by next work shift schedule. It will cause particle variation because particles are everywhere. This is the end of my presentation. Thank you for listening. Maraming salamat po in Filipino or Tagalog. If you have questions, please send me my email as shown in this slide. Once again, thank you very much and stay safe.